We're going on an imaginary subterranean journey around our planet. A remote sensing vehicle will investigate the Earth's crust in close-up. This mysterious layer of rock is all that protects us from the superheated mantle below. It is a fascinating secret world we are only now beginning to understand.
It has been set up like an ancient Egyptian library that we found the door to.
We will uncover the crust's treasures, learn how they get there.
It would be very fast. A crack would open up that would make Mount St. Helens eruption look like nothing.
Discover how the outer skin of our planet preserves and enriches life on Earth.
We are seeing what we think was the start of life.
And reveal new insights into Earth's largely unknown interior. Tautona Gold Mine, about 70 kilometers southwest of Johannesburg, South Africa. An hour-long descent through solid rock carries the workers to the subterranean gold deposits. At 3.6 kilometers down, this is the furthest man has ever ventured into Earth's crust. This rigid layer of rock, on average 30 kilometers deep beneath continents, covers the surface of our planet. But even just 10% of the way down, the miners are starting to experience the extreme conditions of a hidden world. Down in the bowels of the Earth, it's hot. The miners work at a rock face where temperatures reach up to 58 degrees Celsius. About 2 kilometers deeper, and the rock temperature would climb to around 90 degrees.
That's close to boiling point. The rock itself would scald you, making it totally unbearable.
Crushed beneath 3.6 kilometers of sedimentary rock, the pressure down in the mine is almost 400 kilograms per square centimeter. Working under these intense forces is a lethal business. Every day, 5,000 metric tons of ore is blasted from the crust. About 1 ton yields just 12 grams of gold.
Taking out that amount of material rock creates an imbalance in the crust, which causes man-induced seismic events, mini earthquakes.
Around 100 a day, up to a magnitude 4. The miners aren't the only ones who find hidden treasure down here. In the depths of the mine, biochemist Esther van Heerden and her colleagues have discovered life. They call these tiny bacteria extremophiles. Some are an incredible 4/1000th of a millimeter long. Almost 4 million would sit on the head of a pin. Theirs is a world without sunlight or oxygen. Home is 60-degree pressurized water up to 4 times saltier than the sea that collects between the rocks. This is the deepest scientists have ever found life on land. How the extremophiles survive is unique. Radiation from the rocks breaks down minerals in the crust to provide nutrients.
We look at what food is available to them, and all of this gives us information trying to culture the bacteria and to understand what the parameters of life actually is.
The bacteria offer Van Heerden a window into conditions on early Earth billions of years ago. These bacteria could be the origins of life on Earth.
It's very much similar to what we would think primordial Earth would have been like. when we are down in the deep subsurface, we are kind of mimicking or seeing what we think at that stage was the start of life.
The Tautona mine is the furthest that man has ever explored into the rock layer that covers and protects our planet. Until now. Imagine we could take a journey along a tunnel that plots a course through Earth's crust. A rover would beam back images of a unique subterranean trip. It would circumnavigate the planet, traveling over 55,000 kilometers, visiting sites from South Africa to the Atlantic Ocean, and explore the diversity of the crust by burrowing through the rock just beneath our feet. The rover sets a northeasterly course. It leaves the African continent behind as it moves under the Indian Ocean. The rock now changes because Earth has two types of crust. A dense volcanic rock known as basalt forms the crust beneath the oceans. Earth's continents are largely granite rock.
If you imagine that this apple is dense ocean crust and this foam ball is buoyant continental crust, watch what happens when I put them into the mantle, which is the water. The apple bobs deeper into the water than the foam ball, which is why the ocean bed lies lower than the landmass.
Now moving through continental crust at a depth of 40 kilometers, the temperature can reach almost 900 degrees Celsius. You can bake a loaf of bread in your oven at 180 degrees. At almost 900 degrees, rocks will melt. The deeper the rover goes, the hotter it gets. That's because of what's going on inside our planet. Geologist Ian Stewart compares the composition of Earth to a boiled egg.
The shell is like the crust of the Earth, this relatively thin layer completely covering the planet. And it's brittle, which means that if you crack it, it breaks into these big pieces. And on Earth, these are like the big slabs of the Earth's crust, the tectonic plates.
These giant slabs of rock are always on the move, changing the positions of Earth's continents and oceans.
Now, underneath the crust, you get the mantle, which in the case of the egg is this rather squidgy egg white.
At almost 3,000 kilometers, the mantle is a thick layer of rock inside the Earth. It's solid, but can deform like plastic.
The centre of the planet is the core, which for the egg here is the yellow yolk. Now, the outer part of the core is actually molten, it's liquid, but the inner part is under such intense pressure that it's solid.
Heat from the Earth's core creates convection in the mantle that forces magma to the surface. It's like a lava lamp, where heat from the bulb causes convection currents in the oil that push the lava upwards. It's this convection that drives the tectonic plates around the planet. When two continents collide, the crust is squeezed together, thickens and rises up to form a mountain range. The rover now approaches the greatest mountain range on Earth. The vehicle is beneath Everest in the Himalayas. At almost 9,000 meters, it's the world's highest mountain. Here on the Tibetan Plateau, Earth's crust is at its thickest, 70 kilometers deep. It's the result of the continental mass of India crashing into Asia. But what we see at the surface is just a fraction of what's below. A mountain is like a giant ice cube floating in water. The density of the ice means it sits low in the water, with the majority of the cube below the water line. A mountain's density pushes it into the mantle, thickening the crust to form a crustal root. But there's a natural limit to how high these peaks can soar, and therefore how thick the crust can get. Scientists estimate the greatest height a mountain could reach is 15,000 meters, the equivalent of almost 2 Everests. Imagine this play putty as the crust, and this rock a 15,000-meter high mountain. Its weight means that the force on the mountain's crustal root is so great, the root melts and the mountain sinks back down again. The rover heads north on a horizontal course, less than a mile beneath the surface. It begins to move through a shocked and melted crystalline rock, embedded with shards of melted green glass. Here the crust has endured extreme trauma. The rover breaks the surface and finds itself in a huge depression in the Earth. This is Popigai impact crater in Siberia, the result 35 million years ago of a meteorite slamming into the crust. One of the great mysteries for scientists is how Earth came to have 2 types of crust. Early Earth had only oceanic crust, but today Earth also has a continental crust. Planetary geologist Richard Grieve believes meteor impact sites could hold the key. He noticed that there are only about 175 known craters on Earth, while the surface of the Moon is littered with them. The reason for this was demonstrated during the 1971 Apollo 14 mission. When astronaut Alan Shepard hit a golf ball on the Moon, it traveled a huge distance.
Miles and miles and miles.
When Grieve hits a ball on Earth, it travels for meters rather than kilometers. And that's largely because gravity on Earth is 6 times greater than gravity on the Moon. When a meteorite hits the Moon, a lower gravitational force means that, like the golf ball, the debris is thrown clear and travels for kilometers to leave a clearly visible crater. The opposite happens on Earth. The force of gravity pulls the impact ejector back down into the crater.
So if you can imagine that this golf ball here was a piece of rock that was going to be thrown out of a crater. What happens is that it's much more difficult to make a crater on the Earth because of the higher gravity. It's much more difficult to lift this golf ball, this piece of ejector, out of the growing crater.
The result on Earth is fewer craters. When a meteor hits Earth or the Moon, the energy of the impact causes 2 things to happen. A crater forms, and the meteorite shocks and sometimes melts the rock. This leads Grieve to form a new theory. Could meteor impacts have changed the chemical structure of Earth's crust? Grieve investigates this so-called impact melt. He calculates that when large impacts carve out a crater with a diameter of almost 500 kilometers, a tipping point is reached. The amount of melted rock creates a melt pool so great, it fills the entire crater. On the Moon, lower gravity means this tipping point is never reached. Grieve performs a simple demonstration to show what he believes happened on Earth.
Basically what we're going to do is we are going to mix up some butter and some hot water, which is going to melt the butter and form a liquid, and that would represent the liquid from the impact melt. And then we're going to let it cool and see what happens.
As the mixture cools, the butter and water begin to separate and form layers.
So if this was a real case, like on the early Earth, and we'd melted some early crust of the Earth, what you would find is the lighter minerals would be floating towards the top, and the heavier minerals would be floating towards the bottom.
He believes as these pools of rock solidified, the minerals separated to form granite, leaving Earth with two types of crust. The subterranean rover continues its journey around the world, deep within Earth's crust. Now heading south from the Popogai impact crater in Siberia, the vessel approaches the Indonesian island chain of Southeast Asia. As it burrows deeper, it breaks through rock and falls into a slurry of molten rock and crystals. It's beneath Krakatoa volcano, between the islands of Java and Sumatra, the site in 1883 of one of the most powerful eruptions in modern history. For years, scientists believed volcanoes were fed by a giant pipe connected to a vast chamber of magma below. But one man believes they've got it wrong. Bruce Marsh is a geologist with an obsession: magma. For more than 25 years, he's studied the Earth's volcanoes. Like a detective, he pieces together the evidence for the way magma travels through the crust to the surface. His research has earned him the nickname Magma PI.
I had a need to basically find a place somewhere that we could look deep into the Earth's crust, where we could go into the boiler room, look at the plumbing system, look at the heating system, to get an understanding of the style of the system.
Now the rover heads south to the Antarctic. This is where, in 1993, Marsh found his complete boiler room, exquisitely preserved in the dry valleys of East Antarctica. In this cold desert, Marsh can study vast black horizontal stripes, or sills, of solidified magma exposed at the surface.
It has been set up like an ancient Egyptian library that we found a door to. We opened it up, we went in, and our eyes got larger and larger because the scale of the system was so huge that we were not used to understanding a system on that scale and how it all fit together.
This landscape gives him a unique insight into what's happening miles below, to understand how magma travels up through the crust to the surface. These rocks from within the sills are solidified magma packed full of crystals. Marsh traces their distribution across the rock face and finds he can track the magma's route up through the crust.
It's an easier life to think that you have a clean system, a nice pipe going down to a large spherical batch of magma and stuff coming up from another pipe down in the earth. But it's not like that at all.
Marsh built his own system to show how he believes magma moves through the crust. He calls it his magmatic mush column. Water represents the magma. Horizontal glass tanks are the sills, while particles are the crystals. Marsh traces their journey through the crust to the surface.
Take a bunch of sheets, you take a bunch of pipes, you plumb them together a certain way, put some particles in it to see what's going on, and you drive fluid through the system, and it's an eye-opener. You start seeing, and you start believing.
The mush column is proving to be an invaluable diagnostic tool.
By looking at experiments like this, when you go back into the field, you say, now, you know what this is? This is something I saw happening in the mush column experiment tank.
Marsh discovers that magma travels up through the crust like a child's maze puzzle. There is no single pipe connecting the surface to a bulb of magma below. Instead, it reaches the surface along a series of interconnected horizontal sills. Marsh's ideas have revolutionized scientific thinking on the crust. From the dry valleys of Antarctica, the rover continues its journey. Now it heads north. We're under the Pacific Ocean, heading towards one of the most hazardous and notorious geological features on Earth. The rover hits a series of folds and faults in the crust. Our craft begins to shake. 6.5 kilometers down in the crust, the Earth is shifting. It's an earthquake. We've arrived at the highly visible San Andreas Fault that rips through the heart of California for almost 1,300 kilometers. Like a jagged zipper, this giant fracture stitches one slab of the Earth's crust, the North American plate, to its neighbor, the Pacific plate. But the two are moving in different directions. Their movements generate some of the most powerful and deadly earthquakes on the planet.
Windows and everything is falling out. Got a hell of a dust cloud.
How is it all emergency?
Cypress section of the West Grand Freeway has come down.
But scientists have yet to completely understand them. Mark Zoback of Stanford University studies earthquakes. He's one of the world's leading experts on the San Andreas Fault.
We try to model earthquakes. We try to predict how and why they occur. And yet for almost 4 decades, we've argued about the earthquake nucleation and generation process.
Earth's crust is a giant jigsaw of interlocking pieces called tectonic plates. Where the plates meet, the crust is under extreme stress. Given these amazing forces, what intrigues Zoback is why the San Andreas requires less stress than other faults to generate an earthquake. Now, a new discovery at the San Andreas Fault may hold the answer. The San Andreas is a transform fault, where plates slide, shear, or grind past each other. What puzzles geologists is the way the fault behaves differently along its length. The northern and southern parts lock as the two plates slide past each other, building up strain before catastrophically releasing it to produce powerful quakes. Like the one that destroyed much of San Francisco in 1906. Tremors were felt for up to a minute as the quake ruptured almost 500 kilometers of the northerly section of the fault. The central part of the fault is different. It tends to move steadily, producing much smaller earthquakes. Seismologists call this kind of movement creep. June 2004, Central California. Scientists drill a 3-kilometer borehole close to the San Andreas Fault. For the first time, they're able to study rock samples from deep inside an active fault. USGS mineralogist Diane Moore monitors the drilling with interest. Since the late 1990s, she's been looking for the smoking gun, the cause of fault creep.
Finding a weak mineral that would be weak enough to satisfy the low strength of the San Andreas is something we've been doing for a long time, and we're very much unsuccessful.
Among the many minerals she tests is serpentinite. Moore suspects this crustal rock found at the surface of the fault could be a possible cause. But as yet, there is no evidence of its existence deep within the fault. Then, in September 2007, a breakthrough. Scientists begin to recover over 40 meters of rock core from the San Andreas Fault. Principal investigator Mark Zoback is there.
Oh, look at this beautiful rock.
Cross-sections provide a unique glimpse of what's going on deep within the creeping fault zone.
We see ground up rock, what we call fault gouge, and within the fault gouge, we see chunks of this serpentinite floating in this gouge matrix.
That was extremely exciting for me. I immediately sent an email to a colleague down at the drill site saying, I think I've died and gone to heaven.
Moore's suspicions are finally confirmed. Serpentinite exists at depth within the fault zone. When Moore analyzes samples, there's another surprise.
And I was looking at them in the scanning electron microscope, and my eureka moment was finding something that I thought was talc. And that was my moment to, oh my God, this is going to, it is right, it's going to work.
Talc is a watery mineral of magnesium, silicon, and oxygen that forms when serpentinite comes into contact with heated groundwater. Moore knows that talc has a layered structure that makes it weak. Could talc be the smoking gun that proves why the fault creeps to produce small earthquakes? Moore subjects talc to high pressures and temperatures of up to 300 degrees Celsius to mimic conditions in the fault zone.
At those higher temperatures, talc actually gets weaker. The sliding properties are such that it could be weak enough to explain the weakness of the San Andreas Fault. It could also explain the creeping motion.
Zobac's research on the San Andreas Fault has implications for earthquakes worldwide. Scientists like Zobac use GPS data to monitor even the tiniest of movements of the tectonic plates that make up Earth's crust. He's discovering how, curiously, many faults seem to slip without generating large earthquakes.
About 2/3 of the slip occurs steadily, creeping, just like Central California, without big earthquakes. But 1/3 occurs as part of the earthquake process. So this importance of serpentinite and talc may have far greater significance as we look at other faults in other parts of the world.
When there isn't an earthquake along a plate boundary for a long time, scientists often fear the next one will be the big one. But perhaps talc may mean a completely destructive earthquake may not be inevitable. The rover now leaves behind the San Andreas Fault. It sets a course to the southeast towards a region of the crust that contains one of the most valuable resources known to man. Suddenly, our remote sensing vehicle finds itself caught in a trap deep within Earth's crust. The geology changes quickly, without warning, as the crust swings from limestone into sandstone. Like countless prospectors before it, the rover has struck oil. The Earth's crust is like a natural jerry can, only it's immense, holding all the planet's oil reserves until we drill in, satisfying a worldwide daily demand of almost 87 million barrels. The sandstone and limestone here in the Guadalupe Mountains of West Texas looks just like any other rock to the untrained eye. But it can contain one of the most important and precious reserves found in the crust. This is one of the oldest and largest oil-producing regions in the USA. Known as the Permian Basin, 270 million years ago, all this was an inland sea. Compression and heat over millions of years turned prehistoric plants and animals into oil. A great deal of oil. Beneath these towering outcrops of sedimentary rock lies 77 billion barrels of the stuff. Geologists Steve Ruppel and Jerry Bellion are here to survey the area and find it. A laser is fired at the rock to produce a 3D map of the surface to build computer models to deduce what lies beneath.
One of the reasons we really like the Guadalupe Mountains is that what you see exposed on the surface today is pretty much what we see in the subsurface.
What they look for in these stratified giants are reservoirs of oil trapped within the crust. Bellion mixes oil and soda to show how a reservoir forms.
So we'll shake it up.
The oil is less dense than the soda, so rises to the surface, trapped by a layer of impermeable rock, like the cap of the soda bottle.
As the soda and the oil start to separate, the oil will continue to rise until it hits a layer of non-porous rock that will trap it down. So you have non-porous rock above and below your reservoir, which are containing it and trapping it in the subsurface, in the layers of the crust.
Geologists find these reservoirs by hyperspectral imaging. This uses light to bring out details in the rock invisible to the naked eye. The green and purple areas highlight good reservoirs of oil. But it's only because of a quirk in the crust structure that the oil can be extracted. A reservoir can only form in a section of the crust that contains enough holes or pores. It's like pool balls in a rack. If the balls represent the rock, the spaces in between are the pores where the oil collects.
If we look at these rocks right here, we can actually see that a lot of that pore space, is very visible, not only with the hand lens, but even to the naked eye. And it's that abundance of pore space that actually forms a reservoir for the oil to migrate into.
Whether the crust will ever give up all the oil that they know exists here remains to be seen. Next, the rover travels over 1,000 kilometers northeast, burrowing through the Texan oil fields. As it moves through the crust, it encounters a volcanic rock. This is kimberlite, normally found deep within the mantle. The vehicle is inside a dramatic vertical shaft known as a kimberlite pipe. Embedded in its sides are diamonds. But how did they get here? Diamonds begin life as carbon. They can only form naturally over 150 kilometers down in the unique conditions of the mantle. They're stable at a high pressure of up to 60 kilobars and temperatures between 900 and 1300 degrees Celsius. Diamonds are also stable at low temperatures and pressure at the surface. What makes them so intriguing is what happens to them in between. Here at Apollo Diamond in Boston, they grow diamonds. Chief Scientist Patrick Doring investigates the conditions diamonds experience during their journey through the crust.
One of the things that we're interested in is what happens when you heat the diamond away from that super high pressure that keeps it stable.
The diamond weighs in at 1.62 carats. A pyrometer will measure the temperature through the light the diamond emits as it heats up. Doring now subjects the diamond to temperatures in excess of 800 degrees Celsius.
So we're now getting to some of the temperatures a diamond would be subjected to in its journey up to the surface of the Earth.
The heat is soon removed and the diamond is weighed again.
At these temperatures for that amount of time, so about 1,000 degrees C in about 10 minutes, the diamond has lost about 1% of its weight. So you have an appreciable, measurable weight loss.
And its structure has changed too.
The diamond was actually being gasified, oxidized. So what happens is the carbon turns into carbon dioxide because of reaction with the flame.
The next stage in this transformation process would see the CO2 change into graphite to permanently alter the diamond from its original form.
You could see how a diamond, if it's subjected to these temperatures and low pressures for a long period of time, could be completely converted to graphite, and it would never make it to the surface of the Earth.
The experiment reveals that diamonds shouldn't survive their journey up into the crust. So how do they get there? The answer to this may lie on the moon.
Oh, hey, there is orange soil. Well, don't move it till I see it.
The Apollo 17 lunar landing, 1972. Astronaut Jack Schmitt makes a discovery.
Hey, it is! I can see it from here. It's orange.
He finds droplets of glass scattered about the surface.
Fantastic, sports fans. Jack, that is really orange. Oh man, that's incredible.
Today, they're more precious than diamonds. For planetary geologist Jim Head, they're an inspiration.
These are the glass beads that came from the moon. Looking at these and trying to understand how they were in place is what gave us the initial ideas about how kimberlites formed, and in fact how diamonds were delivered from deep within the Earth to the surface.
With little gravity or atmosphere on the moon to shape the droplets into beads, Head realizes they must form deep in the mantle where carbon dioxide plays a part in powering them to the surface.
It was like an epiphany. You just sort of like said, if that works here, maybe that could explain all these issues that are involved in the ascent and eruption of diamonds.
Material from Earth's mantle normally gets to the crust via a very hot and slow process, several centimeters per year. But diamonds would be destroyed if they moved this slowly.
And that's always been the enigma with diamonds. How do you get them to come from great depths to the surface in probably of the order of minutes, maybe an hour? That's been the real problem.
Head develops a theory to explain how a kimberlite forms quickly to blast diamonds upwards. The process starts 250 kilometers down in the mantle, where liquid carbon dioxide forces magma containing diamonds through the rock towards the surface.
When you open a crack deep within the interior, you create a low pressure zone. And when you do that, you actually create a tiny little environment in which gas comes out of the molten rock. That gas then creates a pressure differential that drives that to the surface.
When this carbon dioxide chamber breaks the surface, the fluid expands to become a gas, blasting into the air like soda fizzing out of a bottle, but at speeds of up to 5,000 kilometers per hour.
And then this gas would vent very rapidly. It would settle into a huge jet engine that would just, unbelievable ejection of material into this huge plume that would make Mount St. Helens eruption look like nothing.
A cavity 3 kilometers deep might empty in only 10 seconds, carrying with it diamonds from the mantle. One implication of Head's theory is that an area doesn't need to be volcanic for a kimberlite to form. Diamonds could erupt out of the Earth anywhere. Now our rover sets a course south. We're about to find out what happens when the crust is cataclysmically destroyed. The rover continues its journey. It's traveled over 51,000 kilometers around Earth to reach the Yucatan Peninsula in southern Mexico. It moves from oceanic basalt to continental granite rock. We're beneath a Chicxulub impact crater that straddles land and sea. It was here that a 10-kilometer-wide asteroid slammed into the Earth with energy comparable to 100 million megatons of TNT. That's 6 million times greater than the 1980 eruption of Mount St. Helens in the USA. Planetary geologist Peter Schultz investigates this cataclysmic impact.
It's impossible to even comprehend. The only way we can do this is to do an experiment and slow it down. It's kind of like doing science fiction. You slow everything down.
Schultz has come to NASA's Ames Research Center in Northern California to model the impact. He sets up the experiment. A thick layer of pumice and ceramic microspheres represents the mantle. The thinner layer of pink sand on top simulates the crust. A 3.5-meter-long gun will fire a tiny glass bead at almost 5 kilometers per second into the sandbox. Accuracy is critical. If the sandbox is positioned just a fraction of a centimeter out, the tiny glass asteroid will miss the target.
So what we should be able to see by looking inside is the crater form, and this is like putting unimaginable energy into the crust of the Earth.
The gun is primed and raised into position.
Oh, that's gorgeous. And now what we're seeing is all the vapor, the melt. This is flying out of here extremely high speeds. It's going to go all the way around the Earth and then come back again.
The crater forms quickly, created by the pull of the shock wave as it hits the surface. The impact is so powerful, it punches a hole through the pink crust down into the white mantle below.
What was the mantle is now rebounding. So the crater is turning itself inside out, and it's beginning to heal itself as the mantle comes up.
You can get a similar effect at a swimming pool. Imagine this diver is a meteorite approaching the Earth. He leaps off the board and cannonballs into the water. A spout of water rises in the center. It mimics how the mantle comes up out of the crater.
So the crust originally was bent down, is now coming up. And as this keeps going, it'll continue to get shallower and shallower and shallower.
Remarkably, the crust begins to heal itself. But Schultz believes it wouldn't have happened quickly.
It would have continued for days and days as the entire crater would have continued to collapse because we just created a hole in the Earth that was so deep that it had to seal itself.
Today, few clues of its presence remain at the surface. But its effects were more profound. Scientists believe the asteroid triggered the extinction of the dinosaurs. Is this a glimpse of the cataclysmic effect that follows crust penetration?
Chicxulub was a disaster. We just can't even imagine the shockwave that goes through, the heat, the tsunamis that would have been generated that would have gone all the way around the Earth. It would have been cold, it would have been hot. It's your depiction of Dante's Inferno combined with just frozen hell.
Our subterranean rover is on the last leg of its journey through Earth's crust. It moves on from Mexico, burrowing deep beneath the Atlantic Ocean. We're about to make the most amazing discovery of our entire journey. The rover emerges into water at the mid-Atlantic ridge. 300 square kilometers of the crust is completely missing. This unexpected discovery gives scientists a unique window on Earth's interior, normally hidden by the crust. 2007, marine geochemist Dr. Bramley Merton is one of a team of British scientists who visit the area to investigate. An underwater vehicle beams back side-scan sonar images of the seafloor 3,000 meters below. An area of ocean floor appears to be strikingly different to that around it.
We could see very quickly that this was some kind of scar on the crust of the Earth. The seafloor had a gash, a weeping wound in it, if you like.
Large stripes of rock form a huge dome, 10 kilometers long, 15 kilometers wide.
My team, myself, my colleagues, we've been working on ocean crust for 10, 15 years. Never seen anything like this before. Absolutely stunning, completely gobsmacked.
Rock samples are recovered from this gash in the ocean floor. They reveal something extraordinary.
This mantle rock is one of the most common rocks on the planet, but it's inside the planet usually. To send a grab down and actually pick up a piece of rock from the mantle on the seafloor itself, which could only be a few thousand years old, is really quite extraordinary, quite exciting.
The oceanic crust is missing. Instead, the mantle appears to pop out of gashes or breaks in the Earth's crust. Merton uses an orange to explain.
Now, at the mid-oceanic ridge, the mid-Atlantic ridge where we're working, the crust is split. So if I cut it, it's like a rift where the crust has been split.
At this divergent boundary, the tectonic plates are moving apart at a rate of about 2.5 centimeters a year, pushed apart by heat and magma from the mantle, which moves up to the surface to form new oceanic crust. But here, it's a very different story.
Here, instead of new lava coming out, one plate is being pulled apart from the other, and as it gets pulled apart, here is the interior of the orange, the interior of the Earth, actually being exposed on the sea floor.
Merton and his colleagues are now grappling to understand what appears to be a new process by which Earth's crust is created. It's still early days, but scientists are now considering the grand possibilities of this discovery. It could offer amazing new insights into Earth's largely unknown interior. Our rover's journey is at an end. We've circumnavigated the globe. We've explored for oil, encountered diamonds, alien visitors in Earth's crust. We've journeyed through magma and found talc in the San Andreas Fault, and discovered how the crust contains what could be the origins of life on Earth. The crust is an incredible resource, a myriad of riches. It protects us and supplies us with many of the essentials of life. This imaginary voyage is a journey no one can take, but it reveals Earth's crust to be more than simply the rock beneath our feet.